Hello, everybody. This is going to be a quick video on joined fork loops and their work, span, and ideal parallelism. If you recall, the work is just the total amount of work in your program, in your graph. Just add up all the work and you've got the work. Span is the amount of work on the path with the most work. That's why it's the critical path, is because it has the most work on it. And rather critically, your ideal parallelism, or the best you can possibly hope for, is going to be work divided by span. This makes sense because you're always going to be waiting around for this longest critical path to finish if it's got a set of dependencies and a whole bunch of work on it. The work and span for fork loops is interesting in that if you take a divide and conquer approach, you can get pretty nice span performance. So imagine if you have a fork loop and you're going to fork 8 times in that fork loop. The work would be, if the work was 10 per fork, you would do 80 work in just executing the fork loop, just to get it going. The span, if you divide and conquered it, would only be log of n. So there'd only be 3 times the number of work. So the span would only be 30 as opposed to 80. Similarly, if you did 1,000,000, imagine you have a lot of processors and you're going to fork 1,000,000 times, right? Nicely, that would be, unnicely, that'd be 10 million work to get it going, right? If the work per fork was 10. But honestly, the span would only be 200. It would only be 20 because log of 1,000,000 is about 20. 20 times the work of a fork, so 200. So that's pretty nice. In this example, I have not done 1,000,000. I've only done 8. And the work of each iteration I have here is about 1,000. I tacked on like an extra one to one of them. Obviously, if they were all the same, they each would equally be the critical path length. I tacked an extra one on just so we can sort of see that no matter what, the answers are always the same, whichever path we end up taking, if it takes a little bit more in this case. And you can see here, because we have a fairly nice amount of work, 1,000 work per iteration, given the 80 and 160 if I count fork as 10 work and join as 20, right? I've got sort of 80 and 160 work in just getting things going and getting things joined. And nicely, I get this log performance where it's only 30 and 60 on the span. So, we are getting pretty close to 8 on our ideal parallelism, which is nice, and 7.55, that's kind of nice. Now, if you imagine a situation where we have an unbalanced amount of work, like this is kind of nice, all the work is balanced. If I have an unbalanced amount of work, then imagine this program where we create a parallel for loop, a join void fork loop, imagine it's n long. In this case, we're going to make it 8. And inside, we iterate from j equals 0 to j is less than I plus 1. And we're going to do something, and imagine as 1,000 work for each one. Now we've got this unbalanced situation where the 0th iteration does 1,000 work, the 1th iteration does 2,000, the 2nd iteration does 3,000, right? All the way over here to this last one, which does 8,000 work. Obviously, the critical path length is going to go through here, right? And our span is getting closer to our amount of work here. Like this is starting to dominate a little more. We're not getting this nice 7.55 ideal parallelism over here. Now we're getting like closer to 4.5. And so this is kind of nice. A span in a graph is a perfectly fine term. Kind of like critical path length also, because this is the critical path, right? If you want to improve performance, we need to somehow figure out a way to address this sort of imbalance here. And so hopefully that's a quick explanation of work, span, and ideal parallelism for void fork loops, or fork loops in general.